As Max was saying, I'm Ryan from Modules Labs, and yeah, here to talk about our new proof of concept game on zero-knowledge machine learning, Leela versus the world. So let's get started. So, zero-knowledge machine learning. So I think Daniel talked about this in great depth earlier, but effectively, the paradigm of zero-knowledge machine learning, or at least zero-knowledge inference, is that given some machine learning model, basically such as a neural net or something like that, you can effectively prove in any sort of environment, including an untrusted compute environment, that this is exactly the model which was run to give you the output that you care about. So in our case, we will show that basically the neural network, which is making the moves behind a chess engine, is actually the one doing it, and it's not Magnus Carlsen. Okay. So at a high level, what zero-knowledge machine learning gives us is it enables what we like to call trustless machine learning. In other words, you don't need to trust the model provider. You don't need to trust the environment, again, that this model is running on. All you need to do is trust that your verification process is good, and if it is, then you've effectively run your machine learning algorithm on your own terms. Another way of thinking about this is that these algorithms can run almost autonomously or on-chain in some sense. Okay, and of course the question is, how do we do this? So everyone probably already knows this, but again, at a high level, the intuition is that a zero-knowledge snark is an argument of knowledge. Therefore, it proves to you, as the verifier, that I, as the prover, have some knowledge. Maybe this is like the millionth iteration of SHA for the input cat, or something like that. In the case of computation, however, what we would like to prove is effectively a knowledge of the computation trace. So for all of the steps that I'm supposed to be doing in this computation, I know the intermediate values. And the only way that I could know those values is if I did the computation myself. So these two statements we like to think of as pretty much equivalent. And once you have the fact that zero-knowledge snarks can prove basically some computation was being done correctly, and you think of AI algorithms as basically just deterministic computation for the most part, then you can just see snarks as proving that some algorithm, again, was run correctly. Okay, so that's the premise. Now, basically for us, we like to think, since we are at the intersection of zkAI and machine learning, we like to think very, very hard about what each of these things is good at, and therefore kind of marry the benefits of both. So snarks, of course, are good for ensuring compute integrity. So as we've been saying this whole time, running on untrusted environments, having a trustless, autonomous execution of some algorithm. Now, what is AI good at? I think Daniel gave some great examples. Obviously, ChatGPT is out. Obviously, DALL-E, Stable Diffusion, Midjourney, all these generative models, all these kind of control models are out. But in general, AI has traditionally been good at basically picking up patterns from tremendous volumes of data. So things, algorithms which we couldn't hard code previously, such as recognizing cats within an image or something like that, now all we have to do is just gather a humongous data set, pass it to this model, have some generic learning algorithm, and bada bing, bada boom, this model learns how to recognize the features, sort of the abstract characteristics of a cat. So this is what AI tends to be good at. AI is also good at, in general, optimizing a particular goal. So in the case of, for example, the cat classifier example, the AI is really good at getting very accurate at determining these cats, given that it's learned sort of the features of what makes cats cats. Now, these are sort of, I would say, more traditional kind of classification examples of what AI is good at. I guess folks might know a little bit less about this, but AI, as it turns out, in more recent years, through the paradigm of something called reinforcement learning, has gotten much better at, for example, game playing, such as chess. And so that brings us to basically Leela Chess 0 versus the world, which is our game. So real quick, I guess given this, given these two things which we're trying to unite at a high level, just like to talk about, I guess, zkML as a category. So probably like 7 months ago or so, when we were starting, zkML just didn't really exist, right? You had the tremendous overhead of basically snark computation married or sort of paired with the tremendous amount of compute, which is traditional deep learning. And it's like, that's crazy. Why would you ever try that? But as it turns out, in recent years, snarks have gotten just fast enough to where we can start to do kind of useful things with these models. And that is exactly what Leela versus the world intends to show, which is that you can have a trustless model, which is actually quite performant in some sense. All right, so here is Leela versus the world. It's actually live right now on testnet. It'll be on mainnet very, very soon. But effectively, the game is structured in this way. So you have the world, who is playing the white pieces. If y'all know about, I guess, like Twitch plays Pokemon or anything like that, basically the entire world is playing a single chess game against a singular sort of hyper-intelligent AI agent. It's actually not hyper-intelligent. It's pretty good. But the point is that everyone is sort of voting on moves and trying to collectively beat this agent. So the world is playing white, and Leela, the chess model, is playing black. There's also a betting component on top of all this, so I'll go into this in a little more detail in a moment, but you can see here that there's a prize pool on basically the top left, where you can see how much stake people have put into basically both sides. You have the next move leaderboard under that, which basically shows you kind of all the top moves that people are voting for this turn. And of course, down below, you have your modal where you can purchase power and submit your own moves. Okay, this is sort of the game. Now, let's talk a little bit about the sort of AI model which is behind the scenes and also the tech. So Leela Chess 0 is the name of an open source project in the style of AlphaGo or AlphaZero, if y'all are familiar with these. And effectively, it is what we like to call in the space a reinforcement learning policy network. Now, the details don't matter, or I guess the jargon doesn't matter too much, but you can basically think of reinforcement learning as a different way of training an AI model. So rather than feeding your AI model tons of examples, you can actually imagine your model as sort of like an agent, a baby, if you will, which you just drop into a world. No idea what the rules are, no idea what's good or bad, but in this case, the world just happens to be that chessboard. And then you say to the agent, great, here's your chessboard, here are all the legal moves, we're not gonna tell you how to play chess, you're just gonna figure it out by yourself. And so the agent's going to make random moves, it's gonna get observations, it's gonna make more random moves, and at the end of the game, if it gets checkmated, it will receive a -1 reward, whereas if it checkmates the opponent, it will receive a +1 reward. And so this is kind of the basic framework of reinforcement learning, and it turns out that if you structure this learning in a clever enough way, what we like to call kind of self-play, and also in the case of Leela Chess 0, playing against the community, so playing crowdsourced games against the community, but once you let this baby agent play enough games, it basically becomes a grandmaster. It just picks up patterns in the way that traditional machine learning algorithms do, and it's able to structure kind of very, very sophisticated strategies around this game of chess. And I guess the output, basically, of all this training process is going to be something we call a policy network. So it's just a neural network, just a function that maps from a chessboard state, so this is the kind of the observation or the world that we care about, to a move distribution. In other words, for all legal moves, what is the confidence that this model thinks that we should be playing that move? And so the simple approach, of course, for move picking is just take the argmax over the move distribution and let that be the one that the model is playing. Okay, so that is the sort of chess network. And of course, we would like to make this trustless for the betting component. So enter trustless Leela Chess 0. We actually had to prove a smaller variant for the sake of basically literally provability. But just to give you a sense, this version of Leela Chess 0 has about 3.7 million parameters. It has all the kind of bells and whistles that you might care about in these more modern like convnets, so conv, ReLU, fully connected, squeeze excitation, residual, batch norm, so on and so forth. And all of this was coded, implemented in Halo 2. So this very, very well-known, awesome proving system, and it's actually all being verified via Axiom's fork of the PSC verifier. So all this is already deployed on testnet on-chain. Great. Okay, so this is kind of the trustless tech behind it all, and the way that the game flow works is, so, we enter the arcade modulus. This graphic design artist was really good. Great, so here's our game, and the first thing that you're going to want to do is you're going to want to basically purchase some power. In other words, you want to buy some stake in the game. So power is just how much your vote counts when you are voting for a move. So the more stake in the game you have, of course, the more power you should have to basically influence what votes or what moves the world plays. And the other thing about power is that when you're purchasing power, you can bet on either Leela or the world. So you can actually, in some sense, bet against humanity and say that, yes, this particular AI agent will actually thrash all of humanity at a game of chess. Totally something you can do. Once you've bought power, however, as is shown here, you can basically make a move, and then you can vote on it. And once the entire world is moved, or has voted, the top move basically gets played, and now it's Leela's turn. So this is a GIF, we can't see it. But Leela will be thinking, and in this time period, basically the policy model, or sorry, the policy network is generating what it thinks the next move should be, as well as a proof of inference, which will be verified on chain before that move gets played for black, so that you know that we as the devs are not swapping out this network for a much stronger one, or better yet, just calling up Magnus Carlsen and being like, hey, Magnus, can you give us mate in 3? He's like, yeah, easy. So this is where the sort of trustlessness really comes in. Okay, now none of this would have been possible without our amazing builders and friends. So we would like to thank basically this entire kind of dev community team that's been working very hard with us. Would love to thank Yi and the Axiom team for the fantastic Halo 2 verifier implementation. We actually got the trained Leela chess variant models from one of the Leela chess 0 community members. So thank you to zkAI at GitHub as well. And yeah, Leela is live on testnet, so everyone can go check it out.
Great talk. Time for questions.
What if the human side runs better engines?
Wait, sorry, say that one more time?
What if the world, the human side, if the players stake and run like better engines than
The human side can absolutely use Stockfish if y'all want. Like, you can put in the board state to Stockfish, and then you can play that move. However, there will be people betting against you, i.e. people who bet on Leela. So they will play other moves, and it's really kind of this like social psychology thing as well. And for what it's worth, the Leela chess agent, I think, plays at around 2,000 ELO. So I tested against a bunch of different variants of Stockfish. So it's pretty strong. It's not GM, but it's pretty good.
I think you mentioned the model has 7 million parameters, and there are other LC0 models that have more. What are the future plans for increasing the size, and what are the limitations that exist today?
Yeah, absolutely. So the current model, I think, has about 3.7 million parameters. For us, Halo 2 has been a great proving system in that we can basically encode. So Halo 2 gives you, of course, like custom gates, lookups, all these things. And there are various optimizations, of course, you can do around this. But the thing that we actually run into is a memory bottleneck. So even for kind of the large AWS instances that we were able to rent, for larger models, the RAM usage, unfortunately, was just too high. And so looking into, I think, maybe either other proving systems, so there's a streaming system called, I think, Gemini, which is out there, which are potentially slower, but also use like log space, for example, memory, could be one way of basically scaling this up.